Hello, today's learning intention is to solve two simultaneous linear equations when we are adding an additional unknown to them. Down here at the bottom is an example of what that looks like. So we have two equations, which we have our regular unknowns b and y, x and y, but in this case we've got this third unknown in here. And our goal today is to solve these two simultaneous equations when we are told, or when they have, for some given situation, there could be one solution, there could be infinite solutions, and then there can be no solutions. And there's an example there. I'll find the value of b for which the following simultaneous equations will have no solutions. So what happens as we change the number b, it impacts what those equations would be, and it changes what the resulting lines are. Because these are linear equations, this results in a line, and then this one here results in a line. So if we jump to to Desmos to have a quick look at it, I've put those two equations into Desmos, where it's graphing on an x and y Cartesian plane, and then I've got b set up as a slider where I can change the b to whatever value I want. In this case, when b is just set as 1, we can see that the first equation in red creates one line and then again in the other. But as I change b, these two lines will change. And at the moment, when we talk about solutions for two lines or simultaneous equations, is where those lines intersect. So at this point, they intercept once, so in this situation, by setting b equals 1, we have one solution. As I increase this, let's make b to 2, we still intercept one. It intercepts at a different point, but there's still technically one solution. Then as I keep going, something special happens when I get to 3. It just so happens by setting b to 3, these two lines run parallel to each other. Being parallel with the same gradient means they never have an intercept. So in this situation, these two linear equations turn into a situation where there is no solution, there is no intercept when b equals 3. What happens if I keep increasing b? Well, now they recross, so there is an intercept, and we are back to one solution. And we keep going, still an intercept, still an intercept, and I could keep going and it keeps having an intercept. There also happens to be a particular case. Let's go back. I could set b equal to 0. b equal to 0, they still intercept once, so there's one solution. And if I keep going back and back and back and back, we end up working into this other very special situation where the two lines are actually perfectly on top of each other. That is that they just don't intercept once, but they're intercepting at every single point. Down here at a -5, -4 coordinate, they're intercepting at every single coordinate. That is to say, there is an infinite amount of intercepts, or as we talk about, if I go back to the PowerPoint, they have an infinite amount of solution. That is when the two lines overlap. So now that we've looked at a quick Desmos live example, here's a more detailed breakdown. We get a unique, or in this case we talked about one solution, okay, is when they cross once, right there. Okay. It could happen by changing that variable b. The blue line ends up over here and they cross over here, but it's still only crossing once. So it doesn't matter where it's crossing the once, it's crossing once. And that happens anytime when the two gradients aren't equal. If they aren't equal, they're going to cross. They're going to cross at least at one spot. The other two special cases, which in the previous case that happened at b equals -5, and the no solutions was at b equals 3, if I remember correctly. Okay. Turns out by making b equal to 5, the gradients were the same, or making b equal to 3, the gradients were the same. Both times the gradients were the same, that means the two lines are parallel. It just so happens in the no solution situation, by b equaling 3, the y-intercepts were different. C value ended up different. We're used to thinking, and where I'm coming from all this is y equals mx plus c. If our m's the same value, the two lines are going to be parallel, and then it just all depends on the c value. If the c's are the same, they're going to perfectly overlap. If the c's are different, well then they're going to be separated and they're never going to intercept, so we'll have the no solution. So in these equations where we're going to now look at two simultaneous equations where we have a third unknown, normally it's an A or a B, sometimes a K. The textbook likes to make it M, which is really annoying because you can confuse the M inside the equation with M when we're talking about the parameter for gradient. That can be really frustrating. So it's nice to try and work in a different variable other than M for the third variable. So let's look about how we can go this, how we can find the value of B rather than just sticking it in Desmos and playing with the slider. How can we actually find these numbers algebraically that give us either when the gradients are completely different or the gradients are the same and they overlap when they have the same y-intercept, or they never touch because they have different y-intercepts. So these are the steps we roll through. And here's that example back that I started with. Step one is if the equations aren't written in the standard form of a linear equation, by standard I mean this y equals mx plus c type arrangement. If they aren't written in that form, we need to rearrange them so they are in that form. So both these equations are not written in that form, so we would want to rearrange it for step one. Now step 2 and 3 depends on what we're trying to find. Are we trying to find a unique solution, or are we trying to find when there's no solution or infinite amount of solutions? For no solution and infinite solution, step 2 starts the same way. Once we've rearranged them, we want to compare the two equations by equating their relative m values. And we want to let them equal each other and find when they are equal to each other for that value of b. It'll make a little bit more sense on the next couple slides. From that, you'll generally get two values of b. So in our case, we got b equals 3 and we got b equals -5. And you would have found these algebraically by doing step 2. Once we have that though, you don't know yet, is that going to give you no solution when they're parallel but different y-intercepts, or is it where the two lines perfectly overlap? We find that by then subbing these two values back in for the c's. Okay, so we generally get the two possible b's. We sub one of them in and then check what happens to the y-intercepts. Do those y-intercepts, or what we consider our c value, do the c's become the same or do they become different? If they're the same, okay, we have infinite solutions. If the c value is different, then clearly the lines never overlap. The last one is when we have a unique solution. We actually start with the same step 2 from here. Even though we want a unique solution is when the m's can't equal each other, we use a process of elimination. If I go back to Desmos here, we had it perfectly when b equals -5, and we had perfectly when b equals 3. At every other value of b, doesn't matter what it is, the two lines cross. Okay, so the trick is knowing that fact that apart from the two special situations, every other value for b will actually result in one result. It's most easy, find the two special values of b, and then your actual answer for that will be any other value apart from those two special values. So as it says down here, for unique solution, same as above, but a unique solution will be all real numbers excluding those that produce results, that produce infinitely many solutions or no solutions. Okay, so any number that doesn't result in m1 equals m2. So you find the two numbers that make it work and then just say anything apart from those two numbers. So we work by process of elimination. So the next 3 to 4 slides are a really long worked example. I'm going to roll through this pretty quickly. We've got 10.5 minutes to beat this 20-minute video time lapse. Pause where you need be, but do know that in class we're going to go through a worked example as well. But I do suggest that you pause where you need to at each of these steps, looking at the working out, but I'll go over them as need be. So we've got a new example and we've got actually new equations. Find the values for k for which the simultaneous equations, okay, so we have equation 1 here and we have equation 2 here, so it looks like a bit of a monster. Let's rub that line out so you can actually read it. Okay, have, and then for part I, first part, we're going to try and find when it has no solution. Okay, so for no solution, we need m1 to equal m2. We need them to have the same gradient, but we need the intercepts to not be the same to get no solution. Very first step, step 1 in all of these problems is, are they written in standard form? Or this y equals mx plus c. As we can see, both of them aren't. So working on equation 1 here, all these steps are just rearranging it so that it looks like y equals mx plus c. Same for equation 2, all these steps here are just rearranging it so it looks like y equals mx plus c. And you can see the m and the c1 if you look carefully. I'll draw them out here. Rearranging, that's our first m. Rearranging equation 2, that's our second m in front of the x. So our m is anything attached to and in front of the x. And then we get our c values, which over here we get c is equal to -2, so it doesn't have any of the k's in it. But over here in this second equation, through all the rearrangement, we end up with that being our c. Okay. And that changes depending on what we let our k's equal to. So step 1, rearranging, we now have a new form of equation 1 and equation 2. Knowing that, and we're going back to this bit here, this is what we need. We need our m's to equal each other. So step 2 is we let the two gradients equal to each other. Okay. So m1 is gradient from first equation, that's gradient from equation 1. And over here, this is the gradient from equation 2. So we've just taken those two in the green boxes from this step and made them equal to each other. And now we're just going to solve that problem. Again, it's just a lot of algebra work. This is just tedious algebra work, okay? Solving to find out what k is. So that's just all algebra work. Just this special note here, that although tempting, the 10 and the 2 cannot be cancelled across the equal sign. So some people might say, oh, this 2 here, this 10, I'm going to cancel that, and make that a 5. You can't do that. You can't cancel across an equal sign. So you have to, instead, what we're going to do is multiply this side by 2 and multiply this side by 2. So this 2 and 2 cancels, and we're actually left with a 20 over here. And this side we're also going to multiply by k plus 1. We're going to multiply by the whole denominator. So over this side we multiply by k plus 1. And that's why it ends up there. We expand the quadratic so we can bring the 20 over, and then when we finally get something equal to 0, we can finally use, here we refactorize and then we use the null factor law to solve to find our k values. And as I said before, we've ended up with 2 k's. Okay, so either when k equals -6 in this situation or k equals 3, the gradients will be the same. We just need to know, is that a case of, is it going to be where the two lines are parallel, or is it going to be the special case of where there's one line and then the other line is exactly on top of it? What we want is this situation. That situation occurs when the y-intercepts are different. Our c values are different. So we now move on to step 3. So step 3, we have our 2k values. We need to test them both to see if there are no solutions to the different y-intercepts or the same. So what we do is substitute. We're going to use, let's try k equals -6 first. And we're going to substitute that into equation 1. Okay, or we can substitute it into equation 1, and we're going to substitute in equation 2 the c components. We don't need to do the whole equation. We just need to only do the c components because we've already dealt with m. and we substitute it both in, and it turns out we get -2 for equation 1. This is equation 1, C value, and over here this is equation 2. Substitute, and we end up getting -2 equals -5. So we can conclude if k equals -6, C is different, and if the gradient is the same but C is different, therefore there must be no solutions. And that satisfies what we were trying to find. We were trying to find the k value that results in them having the same gradient yet different intercepts, which therefore means no solutions. Part 2, infinitely many solutions, is dealing with the same thing. We still want m1 equal to m2, which we found before. We know that either occurs at k equals -6 or k equals 3. We've already figured out that k equals 6 gives us no solutions. So we can discount that now. We now need to check, does k equal 3 lead to the intercepts being the same? That's what we're looking for. So we substitute it in to the C component, our y-intercept, the standard form. Substitute it in there, and it turns out that we do get -2, -2. So if k equals 3, it turns out that m1 is equal to m2 and c1 is equal to c2, therefore there's infinite solutions. The very last step is, what if we're asked for a unique solution? So we don't want m1 to equal to m2. So we want the lines to cross, but only cross once. So like we said before, we can use our working. If we ask for a unique solution, then work out the question the same way what we did, but a unique solution will exclude the special cases where m1 does equal m2. So we found out before, if k equals -6 or k equals 3 leads to m1 equals m2, any other number apart from that will lead to this, which is what we want. Okay, any other number. So the way we write that is k is the set of, this symbol means set, okay, or element of all real numbers. So real is any positive or negative, decimal, rational or irrational number. So pretty much any number you've ever been taught of about at the moment, we just use real, the R symbol to symbolize that. But we just need to exclude -6 and 3. Okay. This little note here saying that you need to use curly brackets. So the wrong thing that we see some people do is they go, oh, k is the part of all real numbers except, and this backslash means except, and then they put round brackets, -6, 3, and that would actually mean all numbers between -6 and 3. This would be -6, -5.99, blah, blah, blah. Every number until 3 if you use round brackets. So that would be wrong. That's a quick overview, and that's in 18 minutes. Yeah, there's a lot there. There's a lot of notes, and I've brushed through it, but at least gives you an idea of what we're looking for. There's 3 special cases. Are the gradients different? If they're different, they're going to cross once. If the gradients are the same, they're either going to cross all the time, e.g. they're overlapped, which is infinite solutions, or they're never going to cross, which means there's no solutions. And solution just means how many times do they intercept. And this Desmos is a great way to visualize that. And all we're doing is trying to find these B numbers that give the special case, and then any other B number apart from that gives us at least one crossing point. That's it from me. See you in class.